Morning. My name is Paul Hager. I'm Executive Director of Safe Piping Matters. My organization works to educate and inform the industry on important issues related to piping and plumbing. I really appreciate the time to address you guys at the BSS conference. It's great to be here, and I really appreciate your attention. So we're going to dive right in. We all know that piping and plumbing systems protect our health and safety, but a couple of issues don't get quite the attention they deserve: sustainability and fire safety. So the effect of pipes on these two fronts for any building is significant, and here's your big takeaway. The type of pipes that you have in your building does matter. So here's what we'll cover in the next half hour or so. First, we're going to briefly talk about plumbing systems and materials in general. Then we'll go through some sustainability characteristics of various types of pipe, from the beginnings to the ends of their life cycle. And finally, we're going to talk about fire safety, looking at combustibility, toxicity, and fire stopping. So here are the four main types of plumbing that we look at. Water systems, which supplied water for drinking, washing, and sanitary use. Drain and vent systems, which carry waste away from buildings. Fire suppression systems, sprinkler systems that will slow or stop the progression of fire in a building. And natural gas systems, which of course supply natural gas for heating. So now we're going to talk a little bit about the basic types of piping materials. So there's a lot on this slide, I apologize. The main types of pipes that we look at are copper, which is mainly used for water and gas systems. Iron and steel pipe, which is used for wastewater, but also for gas. Plastic pipes, there's a lot of different kinds of these. We'll come back to that in a second. And they're used in a bunch of different ways in buildings. And that fourth box there talks about failed materials. So that's important, because materials like lead and polybutylene plastic, which are no longer used and are being removed and replaced, can teach us important lessons about what happens when plumbing systems fail in a building. The issue of lead poisoning has received a lot of attention over the last 10 years in the US. It's centered on a little town in Michigan called Flint, which they changed the formulation of their drinking water, the sourcing, pulled it out of a river. And what happened then was that lead started leaching out of their legacy lead pipes in the building, in the ground, and poisoning children, elderly, everyone in town, 100,000 people. And for years, their day-to-day lives have been impacted as they had to drink bottled water, had to have filters, and were waiting for these lead pipes to be removed and replaced. So we had been using lead piping for centuries. We thought it was mostly safe. Turns out that wasn't true. So let's talk a little bit more about plastic pipes, because as we know, there's a lot of different kinds of them. The ones that we tend to focus on are CPVC pipes, which are used for fire suppression systems and a little bit for water systems. PVC pipe, which is used mainly for water and for waste. HDPE, used for water, and the PEX pipe, which is that flexible pipe that runs through generally for drinking water. Each one of these types of plastic has quite different performance and quite different requirements for safety and reliability. And we'll talk a little bit more about that in a minute. So the varying characteristics of metal pipe versus plastic pipe means they do perform quite differently in the field. But what ends up happening is that a lot of design and development discussions center on just one question: cost. How little can we spend to check the box and install a system in a building that meets the presumed spec? These kind of discussions overlook two of our main factors, which are sustainability and fire safety. Let's see why those matter. We'll first talk about sustainability. You may have heard that the construction industry is responsible for 30% of the world's energy use and emissions. I actually heard in the previous session that it's more like 40% or even more than that. But did you also know that construction is responsible for a huge amount of waste production? I'm sure you've thought about that, but in fact, in the UK, the construction industry is responsible as the second largest producer of plastic waste in the country, generating about 50,000 tons a year of plastic alone. So what this means is that if we want to move toward a more sustainable future, we need to improve how we design and build buildings, and that includes the piping systems. So the UN has been looking at sustainability for decades. And about 40 years ago, in 1987, they defined sustainability as doing things now that will enable the generations of the future to live and work productively. What that means is we have to stop producing things in a linear fashion, where we extract materials, create something, and then produce trash, and move toward a circular economy. There's a lot of discussion of what that kind of circular economy is going to look like. I don't think there's a lot of answers. But we need to make sure that we're reusing more materials and creating smaller carbon footprints. Otherwise, those future generations are going to have a big problem. So in order to understand what that means for piping, we need to look at the life cycles of the materials. What happens when the material is produced? What happens to it in use? And what happens at the end of life? We're going to start with copper. So copper has been used in plumbing for hundreds of years. You have to say, the extraction of copper from the ground and refining the ore into ingots and then producing them into products, all that has environmental impacts. It also has a carbon footprint. That's true. However, once you produce carbon, it's there. It can be reused basically infinitely. The copper that was produced in Roman times can still be used today. And some studies show that 2/3 of all copper ever mined is still in circulation. Major copper producers also have been transparent about the impacts that they're having, and they've subscribed to something called the Copper Mark program, which is an independent body that they've set up to track their progress against UN Sustainable Development Goals and require themselves to improve their operations and reduce those impacts. In use, copper piping performs very well. It can last for decades, often beyond the life of a building. That's true for a lot of piping materials. They often outlast the life of the building. The metal in copper pipes is highly stable. It doesn't leach chemicals into drinking water. That's a good thing as well. And copper pipe is highly repairable. Does require training. You have to figure out how to solder and braze the stuff, but you can repair it. Here's a big point. At the end of its use, copper retains its value. That's not just financial value, although that is very significant, but it also retains all its performance value. Has the same stability, the same ductility, and the same performance characteristics that it did when it came out of the ground. And that happens again and again and again. So reusing this resource not only reduces the amount that we have to take out of the ground, but it also reduces the amount of energy that's consumed to produce the product again by 85%. So now let's turn to the life cycle of iron and steel pipe. To be honest, it's very similar to copper. So you still got to take it out of the ground, you still got to refine it. Those have environmental and energy impacts. In addition, the weight of iron and steel is significant, so that means it costs a little bit more to get it from point A to point B. On the other hand, though, that weight comes out to be a real advantage for many of the applications where iron and steel pipe is installed. Often these installations are below grade. They might be running under concrete. They might be running under the foundations of a building or under paving material. The fact that this material is so heavy and strong means that it will not deflect or crack the way some other materials will. And just like copper, after use, the iron and steel industries have set up mechanisms to reclaim and reprocess their materials. The Iron and Steel Institute pegs the recycling value of steel, the recycling rate of steel at well above 60%. Another good part about the strength of iron and steel is that when it's installed, let's say in that middle picture, you see a sewerage pipe that's installed in an exposed parking garage. If a truck or a car happens to bump up against that, it's not going to break. If you're in a stairwell and somebody's loading gear up that stairwell and they happen to bump the pipe, it's not going to break. Now we'll look at the life cycle of plastic pipe. Just like for metal, the extraction and production processes are significant. They're not coming from mines, they're coming from drilling for oil or fracking for natural gas. That produces the feedstock, the little plastic pellets that are then formed into products. That impact means that you have a very significant carbon footprint for plastic. What's probably more troubling than that piece is the fact that plastic growth has been generally unfettered over the last several decades, and it's projected to grow 5 times by the end of this decade. What does that mean for plastic pollution? What does that mean for the carbon emissions and footprint of the plastics industry? In use, the different types of plastic, especially in the building industry, make it a little difficult at times to know what's an appropriate use. I was talking with a gentleman earlier, and he said often what he sees on job sites are a little bit of this over here, a little bit of that over there. It's pipe, right? That doesn't guarantee that it's going to perform reliably and over the long term, or that it's going to be safe. For example, PVC can't be used with very hot water. It's also damaged by UV light, so if you put that in an area that's exposed to sunlight, it's going to degrade over time. HDPE pipe has significant thermal expansion and contraction factors. So if you put that into an unconditioned space, let's say an exterior wall or an unconditioned plenum, you better account for that expansion and contraction, otherwise you're going to stress your fittings or come outside your safety zones. Another interesting or challenging piece of understanding the different types of plastic is what kinds of chemicals can you use around them. Chemical compatibility, if you look at the guidance from manufacturers, their lists of base chemicals are pages long. You need a spreadsheet, and you need to understand and instruct your building maintenance teams what they can or can't use around certain types of plastic pipe. That includes things like solvents, things like lubricants, things like fire-stopping substances, mold abatement, HVAC, heating and cooling fluids. You can imagine the kinds of accidents that can happen over the life of a building when you have plastic pipes in vulnerable positions. And then, of course, not to mention the physical impacts, like you can see on that pipe on the right. Something probably fell on it and broke it. And then we're going to talk at the end a little bit more about combustibility of plastic pipe and why that matters. So the most significant impact and difference of plastic pipe comes at the end of the cycle. I heard a talk earlier where they were talking about the circular economy and what happens to plastic pipe at the end of use. Sounds like they're trying, but in reality, 0% of plastic pipe is recycled. It's not 2/3, it's not 60%, it's 0%. In the US, you're not even allowed to recycle PVC pipe because it will cross-contaminate into water systems. What that means is at the end of life, plastic pipe either gets landfilled, increasing plastic pollution, or it gets incinerated, increasing emissions and carbon footprint. So looking across all the different types of plastic pipe, it's clear that at the end of life, you have a really big difference. Some of these products are linear. You extract them, you use them, you throw them away. and some products are actually circular. So let's turn now to the issue of fire safety. How do these products perform installed if there is a building fire? That comes down to one basic characteristic: combustibility. So here's a chart showing various temperatures at which different piping materials will melt or burn. For reference, the average temperature of a structural fire is about 1,500 degrees Fahrenheit. So you can see that most of the metal, well, all the metal pipes fall above that threshold, and most of the plastic pipes fall well below that. Starting at about 400 degrees, that plastic pipe is going to catch fire, especially if it's in an exposed space. So I also just want to point out the thermal expansion factor that I talked about before with HDPE pipe. You can see the factor of difference between metal and plastic there. So how do these numbers end up translating into real life? Here's just one example. On the left, you can see a water main, HDPE water main, that, if you can believe it, they decided to install above ground in a wildfire-prone area of California, experiencing historic drought. And surprise, surprise, when a wildfire hit, the thing burned. Miles and miles of it burned. This left Santa Rosa, thousands of people in Santa Rosa without water for months. And even when the water line was restored, the benzene that had leached out of these burned and melted plastic pipes had contaminated their water system. So all the absorbed benzene and other carcinogenic VOCs were inside their pipes. They got to remove and replace them at a cost of millions. So here's another example the gentleman talked about before, Grenfell. This is not related to piping at all, but it is an illustration of what happens when plastic materials are used in a way that causes issues. Here you had a plastic foam sandwiched between some aluminum, and when that caught fire, the burning plastic increased the temperature of the fire. It helped spread the fire across vertical floors of the structure, and you can even see it in this picture, it generated a lot of toxic smoke. In this tragedy, 70 people died, and the fatalities continue even today. One of my colleagues recently sent me a story saying that 12 of the firefighters who fought in this fire have been diagnosed with cancer that likely came from their exposure to chemicals released in the smoke. Here's another, possibly the most striking illustration I've ever seen of research that shows what happens when you plasticize the built environment. The Fire Safety Research Institute recently completed a study a couple years ago. On the left side, you see a natural room. This is a room from the 1960s. If you haven't seen this video, please look it up, Google it, Fire Safety Research Institute, it'll pop right up. So the 1960s environment, natural materials, wood, metal, natural fibers, cotton and wool. On the right side, you had more synthetics, polyester, plastic foam inside the cushions. When that caught fire, initially, the room on the right, for the first minute or so, was smaller flames. But within 5 minutes, that room was fully engulfed. You can see what it looks like now after 3 minutes and 48 seconds. So despite the presence of fire retardants in these materials, the products burned. What happened on the other side, the natural room? After 29 minutes, it was still not fully engulfed in flame. What does that mean for the risks of the people who might have been in that room when the fire occurred? What does it mean for the risks of firefighters, or the chances of firefighters getting to a fire within 5 minutes, by the way, on the synthetic side, to put out that fire and stop it from engulfing the building as a whole? So let's remember, plastic pipes are made of plastic. they will burn, starting with the exposed piping and then moving up into the walls. So we talked a little bit about the toxicity of what happens to plastic when it burns. There's been a lot of research on this, and they burn plastic pipes, capture the chemicals, the smoke that comes off of it, and analyze it with spectroscopy. And what did they find? They found a large presence of VOCs and SVOCs, and they also found some lovely toxins like formaldehyde, cyanide, together with all the normal stuff like carbon monoxide, sulfur dioxide, etc. University of Purdue professor Andrew Welton also has looked at what happens to plastic pipe when it melts or burns, and then what chemicals it releases into water. We talked a little bit ago about the Santa Rosa fire and the presence of benzene there. He showed that in another wildfire, benzene coming from plastic pipes exceeded 40,000 times the safe limit of benzene that got into the water system, and again, couldn't be flushed. They had to remove those pipes and replace them. So if you get exposed to these chemicals, what happens? In the short term, you can have some quite acute health effects. So things like nausea, throat, lung irritation, etc. It's the longer term health effects that we're starting to see now, and we've got an unfortunate sample with firefighters. And the graph on the left there shows the increase in firefighter cancers since the 1950s. Not coincidentally, that roughly corresponds with the increase in the use of plastics in the built environment over that same period of time. These firefighters, otherwise generally healthier than the normal average public person, are coming down with cancers of the brain, cancers of the reproductive system, cancers of the liver and the kidneys, all these organs that are exposed to these toxins over time as they breathe the smoke or get soot absorbed into their skin and get exposed to the toxins. So now let's talk a little bit about fire stopping. Fire stopping is quite a technical application. Sometimes it's done right, sometimes it's not done right. Very often, even the inspectors, I've been told, don't exactly know what to look for, because every single system is prescribed for a particular material and a particular spec for operation. For plastic pipes, the fire stopping degree of complexity is much higher than it is for non-combustible metal pipes. So you have a material that's going to burn or melt, you better make sure that you fire stop that carefully, because if there's a hole in a firewall that's meant to block fire from moving from one area of a building to another, and it gets a hole in it, that firewall might as well not be there. So we'll now take a look at what happens if you don't do it right. So here's a list of critical fire stop failures that people often see in the field, from using the same system across all different types of pipe to just not executing a fire stop for a particular piping system correctly. As we noted, plastic is a more complicated material to fire stop around because it's combustible. And in fact, in this picture, you can see that the collar, the orange collar around that pipe in the middle, is not secured to the wall. Should be, because the intumescent foam that's meant to compress that pipe compress that pipe to seal off the opening in a fire, what happens to that if it expands and the collar isn't secured to the wall? It just pushes out both sides of the wall. Now the pipe can burn. There's a large hole in that firewall. And studies show, I think I showed this on the earlier slide, that even a pencil-sized hole in a firewall can allow smoke to come through to the next room in just minutes. So I think what this calls into question is as we build buildings, should we be putting higher degrees of complexity and difficulty in for critical life safety systems? A lot of critical buildings like hospitals or tall high-rises don't allow plastic pipes in them for just this reason. It's just too risky to put in plastic pipes that are difficult to fire stop. But should we be limiting that even more? I think the answer is probably yes, if you believe that some of this fire stopping is not being done right. So I think we're down toward the end of our time, so I'll quickly sum up before answering any questions that you all have. So we talked about how the materials used for piping have big impacts on sustainability, from the beginning to use and to the end of their life cycles, whether they can either be reused or if they're going to be trashed. Then we talked about the importance of combustibility of pipe and what impacts that can have on life safety and health in the short term and in the long term, both for individuals like firefighters or for whole communities like Santa Rosa. And I think all of this, and then we talked a little bit about fire stopping and some of the challenges around that. I think what all this raises for me, and I'll leave you with this final thought, is we learned some lessons from lead piping over the course of centuries, right? What questions should we be asking and deriving from research that's being put out today, some of which I showed you, about current piping systems and the degree of safety and sustainability that they offer? So with that, thank you very much. I appreciate your time.